If you write software, you have probably set a socket option once and never thought about it again. One line, setsockopt, comma, IP underscore TOS, comma, some number. And then you moved on because nothing visible happened. Today I want to show you what happens to that number after it leaves your process. Because it does not disappear. It gets read, it gets judged, and on a good network, it decides whether your traffic goes first or it waits. We have 4 applications running over a segment-routed MPLS core. Every one of them asked for something different. We're going to follow that request from the socket out to our edge router, across the core, and back out the other side, and see exactly where the network agrees with your application and where it overrules it. What we have here is client 1, and on client 1, we're going to go ahead and we're going to show you what these 4 applications are. Each one declares its own priority in its own source code. This is the part software engineers control. Command and control messaging marks itself CS648. Small messages, not much of them, but they must never be late. The track feed marks itself AF31, 26, steady, moderate, drives a map display. Full motion video marks itself AF41, or 34, fat, and it hates jitter. An imagery push marks itself CS1 or 8. That is below best effort. On purpose, it is a bulk file transfer. It is the elephant and it knows it. Hold on to that last one because we're going to come back and make it lie. What we'll do now is we will search and display the entire mechanism. And it is 6 lines of Python. So we'll go ahead and clear our screen. You take your DSCP value and you shift it left by 2 because DSCP is the top 6 bits of an 8-bit field. The bottom 2 bits belong to the explicit congestion notification, otherwise known as ECN, but that's a different conversation. Then you hand it to setsockopt as IP underscore TOS. That's it. That is the whole contract between your application and the network. 1 byte in the IP header. No negotiation, no handshake, no acknowledgement that anyone is listening, which raises the obvious question. Is anyone listening? In client 1's terminal, I'll go ahead and I'll run the command, which is technically 1 line, but with 2 things happening. It starts a packet sniffer on the wire, and it waits 2 seconds so the sniffer is listening. Then runs the command and control app, which asks for CS6, which is the DSCP marking. The table at the top is the sniffer. The 2 lines underneath are the application reporting what it did. And there we can see it, CS6 or 48, on every single packet. It's read straight off the wire. On the wire that is the byte 0xC0. Because 48 shifted left by 2 is 192. The kernel did exactly what we asked and put our number into the header. So the application asked, and the operating system delivered. 2 stages, done. And neither of them involved the network at all. Everything from here is someone else's decision. So we can see what happens locally. But how about on the network itself? So what we're going to do now is we're actually going to fire up Wireshark. And we're going to do so in between our edge router and our provider edge router. So we'll go ahead and we'll start a capture. And inside of our capture, we'll go ahead and filter for DSCP field 48. And the way we do that is using our filter line. And then we'll go ahead and click enter. Now from here, we'll head back over to our client and we'll run the command to execute our Python file for our messaging app. So let us stop talking and let's see what the actual packets look like. So this is a capture on the LAN link between the customer router and the edge router. Plain Ethernet, plain IP, nothing exotic at all. So you see my filter up top, that is CS6, what the command and control app asks for. And there are the packets. So now we'll go ahead and we'll look at the IP header. So what we can see here under the IP header is our differentiated services field. And what we can see is 0xC0 and DSCP CS6. That is your setsockopt call rendered as a hex byte on a wire, being carried by hardware that has never heard of your application, and nothing has judged it yet. This is a request in its pure form. We'll go ahead and we'll leave this capture running, but we're going to start an additional capture. And what we're going to do is we're going to actually start this on our segment routed MPLS core between our PE1 and our C1 router. So we'll go ahead and we'll start a capture here. This one is actually on the segment routed core. And what we'll do here inside of our display filter is we'll just type the filter of MPLS. And then we'll come back to our Linux shell and we'll go ahead and we'll rerun this command. So it's the same traffic, the same application, it's just one hop later, and it looks completely different. So if we click a packet here, once we can see our screen, so now what we can see is the multi-protocol label switching header sitting between Ethernet and IP. In other words, it's layer 2.5. So we'll go ahead and expand it here. We do see 2. So this is the label. That is the segment routing label identifying the far end and the time to live. And the field I care about, which is our experimental bits, also called traffic class. And as we can see, they are here. And what we can see is a class of 6 here. So what I'm going to do is I'm actually going to expand our filter option here. And this is the filter, which is the entire point of the video in one line. So as we could see, the MPLS experimental bits equals 6. This is the network's decision. It's 3 bits written by the edge router when it classified our traffic as network control, which is our most important traffic. In other words, our IP.dsfield.dscp equals 48 is the application's original request still sitting in the inner IP header completely untouched. So both match. It's the same packet, it's just 2 different fields saying the same thing in 2 different vocabularies. And this is what a core router actually reads. It looks at these 3 experimental bits and nothing else. Your DSCP is still there. It is just being carried as cargo. The core is not inspecting your application. It is trusting a note that the edge router pinned to the outside of the envelope. Now, how does our actual LAN edge router read our packet? So what we're going to do here is we're going to go into PE1, which is our provider edge. And we're going to go ahead and we're going to run the command to actually see our class of service that is on our gigabit Ethernet 003 interface, or sub interface, I should say. So this is the LAN edge router. This interface is the one facing your customer site, and it is the first device in the world that has an opinion about your byte. So the 2 objects are attached, a classifier on the way in and a rewrite rule on the way out. The classifier is the one that matters right now because that is the network reading what your application actually asks for. Now what we'll do is we'll open this up a bit. And here is the actual translation table. This is the moment your socket option becomes a routing decision. CS6, our command and control traffic, that becomes network control. And it is our most priority traffic on the network. So you also have EF, and that becomes priority traffic. AF41 and AF31 both become shared forwarding. This is just describing precedence and packet prioritization. So you also have CS1, our bulk transfer, and that becomes best effort. Look carefully at the 3rd line because it is the first honest disappointment of the day. Your video application asked for AF41 and your track feed asked for AF31, which are 2 different requests. Your network has 1 queue for both, and it collapsed them. That is the part that surprises most people. You have 64 possible DSCP values. This network has 4 forwarding classes, and your application's vocabulary is much richer than the network's. And the edge router is where that vocabulary gets truncated. So now I want to actually see what end-to-end really looks like. So I'm going to do a few things here. On client 2, which is our client on the receiving end, I'm going to go ahead and run a Python script that we have created here. And we're going to leave this running. This is the receiving end. And what it shows is, per stream, what the application asked for and what actually arrived. It also has to be running before the next command because the imagery transfer is TCP and it needs something listening to connect to. Okay, so back on client 1, we'll go ahead and we'll rerun our command. Let me go ahead and clear this screen. So we'll go ahead and rerun the same command as we had before. Now we're pushing imagery. And what we're going to see is the interesting part. That is our bulk file transfer, the elephant. This is the large file. I have just told it to stop being honest. With the greedy flag, it marks itself EF or 46, EF46, which is expedited forwarding. the code point you reserve for voice. A bulk TCP transfer just claimed it is real-time traffic, and nothing in your application stack can stop it, because the application is the thing doing the asking. Any process on your network can set any DSCP it wants. So when we watch the receiving console, it asks for EF46, as we can see here. But it arrived as CS1 or 8, and the console has flagged it and remarked it at the gateway. So now what we'll do, we'll go back over to our PE1, which is our edge router again. We'll go ahead and open it up a bit so we can see. And now what we're going to do is we're going to look for a firewall filter that we did configure. This is going to clear up why we just saw what we saw. A filter, which is on the LAN edge interface, which is match the TCP on the imagery port, forcing the forwarding class to best effort. And it rewrites the DSCP to CS1. And it accepts it. The edge router did not argue, and it did not drop the traffic. It simply declined to believe it. Your bulk transfer still gets delivered, which it did. It just gets delivered at the priority it deserves rather than the one it claimed. So in other words, it lied and said it was the most priority traffic, but we all knew it was not. This is the trust boundary, and it is the single most important idea in this whole video. Marking is a request. The edge is where a request becomes a decision. Now, the next piece of this is trying to catch the lie in flight, okay? But we have to do some prep work here. So what we're going to do is we're going to look at our captures that we had before. So to start, we're going to go to our capture between PE1 and CE1. So let's find that capture now. So this is PE1 to CE1. And then what we're going to do is we're going to implement some filters here. So we'll go ahead and clear this filter, and we'll press enter. And notice we have a blank screen. Now we're going to go from PE1 to C1. So we'll go ahead and we'll find that filter or capture. So PE1 to C1. Now we will implement the following filter here for our TC port, which is 9300. That's by design. And as we're going to see now, we're going to go back to our client 1. We're going to clear our screen, and we're going to go ahead and we're going to run our script to be greedy. Now, the one thing about this is we still have to have our TUI that is tracking this on our receiving side. So when we try to watch both captures at once, because this is the same TCP flow entering and leaving the same router, we'll go ahead and we will pull these up side by side. On the left, the LAN side, filter is TCP port 9300 with DSCP packet 46. Packets are matching. It's actually on our right side. Our bulk file transfer is arriving at the edge router claiming to be expedited forwarding, right? Which we can see here. On the left, the core side, same flow, no DSCP filters at all, so we can see whatever it became. And we can see that the EXP bits are in fact 0. So that's best effort. That is not EF. Now we look at our inner IP header. Our DSCP is now 0x20, as we can see here. And what you can see is a DSCP value of 8, or otherwise known as CS1. That is the same TCP connection. Same source port, same sequence numbers, and between one interface and another, it was demoted. On the way in, it said EF, or expedited forwarding. On the way out, it said CS1. And the label says best effort. The application lied, one interface caught it, and the correction is visible in the packets on both sides. If you ever wondered whether quality of service policy is real or just documentation, this is what it really looks like. So now what we'll go ahead and do is between our PE1 and C1, so that's here, we'll clear our filter, and we'll actually open it up because we want to see a diffserv code point of 8, or an EXP bit of 6. So we'll close the loop, and here's the corrected traffic isolated, which is EXP0, DSCP CS1, agreeing with each other, and the network reached a verdict and wrote it down in both vocabularies. Let's tie it in a little bit. So this is our core 1, and we're going to go ahead and implement the command to show our class of service on our interface gigabit 001. So this is our core router. Notice what it has and what it does not. it has an EXP classifier and an EXP rewrite. It is reading 3 bits out of a label, making a queuing decision and writing 3 bits back. It never opens the IP header. Your DSCP value is still in there, untouched, and it's riding along as a payload. The core is not ignoring your application's request. It is acting on a summary of it that the edge router wrote down. Now we'll run over to PE2. And on PE2, we'll look at the actual rewrite for our egress. We'll open this up. So this is our far side of our network. I want you to see this because the label comes off here. In other words, the MPLS label pops. And once it pops, it goes back to IP traffic. So this router has to turn its internal decision back into something that the receiving application can see and understand. Network control goes back out as 110000CS6. All right. Premium goes back out as expedited forwarding. Assured forwarding goes back out as AF41. And best effort goes back out as CS1. So here is the second honest disappointment. So if we look at assured forwarding, anything that came in as AF31 will leave as AF41. The track feed asks for AF31, but it got merged into one queue with the video, and it comes out the other end wearing the video's label. The network did not preserve your distinction because it never carried your distinction. It carried its own. Now what we're going to do is we're going to run some GNS3 magic, and we are going to actually access all of our routers that are running inside of our virtual workspace. So what we're going to do is wait for this code to execute and read off of the routers themselves. Here is all 7 stages in one place, and it's read live off of our routers. The application asks for CS6. The kernel wrote 0xC0. The LAN carried it unchanged because switches and routers do not rewrite what they are not told to rewrite. The gateway classified it as network control. That collapsed it into EXP110 for the core. The core acted on the label, not the IP header, and the far edge translated it back to DSCP48. One command, one round trip through everything we just walked through. And read the note at the bottom because it matters. Stages 4 through 7 are configuration read from the routers. This tells you that the network is wired correctly. It's not a packet caught in the act. For that, you need the receiving console we ran earlier and a capture on the core link. Never let a tool tell you that traffic is behaving when all it has checked is its intent. So now we're going to go ahead and go back to our client 2. So what you should actually take away from this as someone who writes software. The first is your marking is a request, not an instruction. Setting the IP_TOS cost you 1 line. And it's worth doing because a network that is configured to listen will listen, but nothing guarantees it. Second, the trust boundary is real, and it is close to you. The first router at your site decides whether to believe your application. If you mark everything expedited forwarding because you think everything is important, you will be caught, and you will be remarked, and you will have spent your credibility for nothing. Third, the network has fewer classes than you have opinions. 64 code points, 4 queues, 3 bits in the core. Pick a small number of meaningful classes and use them consistently, because the ones you invent beyond that will be merged whether you like it or not. And finally, ask your network team what the classifier on your edge router actually says. It's one command. It is the exact table that decides how your traffic gets treated. And most engineers will have never seen the one that governs their own applications. For copies of what we did here, please reach out to me. I can provide them at will. I am not a software engineer, but at the end of the day, what we did was a basic write inside of an application to display how DSCP and a type of service can be configured and marked and handled by your network. So I thank you for your time, and hopefully you got something out of this.